Oh, quick little story I told last year, I'll tell again. When I was in middle school, I discovered this little concept. And with a whole bunch of balloons, I rubbed them on my head and stuck them to the ceiling in my house. And there was a couple of balloons. One in particular was one of the balloon animal making balloons. It was a long, skinny one, stuck to the ceiling for, I believe, 2 months. And one of the things we discovered after we took the balloon down is that dust carries a charge. And we had adhered the dust to the ceiling. When we took the balloon out, there was a shadow of the dust in the ceiling that was there for probably a decade. So just an of note, you might not want to do that. All right. So now, charge is quantized. Charge is quantized. What does that mean? For something to be quantized, a silver.
You can measure it numerically.
I agree with that, but there's actually more to it than just saying you can measure it numerically. No.
It has whole number values. You can't have like half a charge.
You can't have half a charge. It only comes in discrete values. Charge is quantized. It comes in specific discrete quanta. What is the quantization of charge? What is the minimum charge you can have? What are the intervals of charge? It's not a Coulomb, actually.
Would it be like 1 electron?
1 electron or 1 proton, depending on whether you're talking about positive or negative charge. So it comes down to the fundamental charge. So charge is quantized in that the charge on an object, Q, is equal to n times E, where n is an integer, and E is the fundamental charge. The fundamental charge is positive or negative 1.60 times 10 to the negative 19 coulombs. Coulombs. So we have a new dimension for this semester. It is coulombs. So 1.60 times 10 to the negative 19 coulombs, positive or negative, of course, depending on whether we're talking about a positive proton or a negative electron. So that's what it means that charge is quantized. You can't have, for example, something with a charge of 1 times 10 to the negative 19 coulombs. You can't even have one that's 2 times 10 to the negative 19 coulombs. You could have 1.6 times 10 to the negative 19 coulombs. You could have 3.2 times 10 to the negative 19 coulombs. But you can't have 1.5 electrons, for example. It has to be an integer multiple of electrons. One thing to make sure that you understand is that this is not a base unit. Coulombs is not a base SI unit. For some reason, amps are the base SI unit that has coulombs in it. We clearly haven't done amps yet this year, but you did them last year, and we'll get there in soon enough, I guess. All right. We need the term point charge. A point charge, just like a point mass, is an object that has charge, but the size and shape of the object, the size is small enough and the shape we consider to be a sphere. It's something where the charge is large enough where the shape of the object doesn't matter. We can consider it to be a sphere. So we're going to deal with a lot of point charges in this class. And we have a force of attraction between, or repulsion between, point charges. Going back to the law of charges, the equation is the electric force is equal to, actually, that's not the way it's done in this chapter. So force 1, 2 is equal to K times Q1 times Q2 divided by R squared times the unit vector R. So this is called the Coulomb force. And K is called the Coulomb constant. And K has a value 8.99 times 10 to the 9th newtons times meters squared divided by coulombs squared. This equation should look very similar to one we've worked with before. Which one was that? Meg?
Force gravity.
The universal law of gravitation. So K is a constant, just like big G was a constant. Instead of having mass 1 and mass 2, we have the charges, charge 1 and charge 2. We also have R, and it's the exact, well, very, very similar. So let's review. Class, R is not, it is not between the center of masses, the center of charge of the two charges. This is especially confusing because R sometimes is. So again, by definition, it's not the radius, it's the distance between the center of charges of the two charges, but sometimes it does work out to be the radius. One major difference between this equation and Newton's universal law of gravitation has to do with direction. Notice with Newton's universal law of gravitation, it was always an attractive force. With the Coulomb force, it is not always an attractive force. You can have unlike charges attracting, but if you have like charges, they're going to repel. So it's something to keep in mind here. Please find this equation on your equation sheet. Who found it? Miller.
The first one.
Is that equation on there?
Not exactly.
Not exactly. So let's discuss the differences. The equation on the equation sheet does not use Coulomb's constant. Instead, it uses the permittivity of free space, which is 1 over 4 pi E naught. So it uses this thing with this E naught, which is called the permittivity of free space. Which I believe is 4 pi times 10 to the negative 7. But we're not really going to go through permittivity of free space. We don't really go over this just yet. We'll go through this when we get a little bit farther into the class, but it's important to realize that when you're looking at your equation sheet, they use 1 over 4 pi E naught instead of the Coulomb constant, but it works out to be the exact same thing.